To gain a better understanding of what sound waves are, we're now going to look at calculating the maximum displacement in a sound wave. Remember, pressure waves are really what sound waves are. So we have a continuous pressure wave, continuous buildup of pressure in rarefactions, regions of high and low pressure through the air that move through the air at the speed of sound. Remember that the molecules themselves are just slightly displaced from their normal position by very small amounts, causing these variations in the pressure which rush through the air. Notice that this is a nice representation of how the pressure changes, and we have an equation defining the change in the pressure like that. And then we have the corresponding displacement of the molecules, and notice that they're offset by 90 degrees. So here's the equation describing the displacement of the molecules from their normal positions. And notice that the only difference is that this is a sine function, that's a cosine function, which makes them 90 degrees out of phase with one another. We found an equation that describes how you calculate the maximum pressure difference, and if we take that equation and solve that for the maximum displacement, and given some parameters, we can find out what the maximum displacement would be. So let's say we have a wave where the maximum displacement, not the maximum pressure difference, is 0.02 pascals, so 2/100ths of a pascal. The density of air, typically about 1.29 kilograms per cubic meter. The velocity of sound in air, 340 meters per second. And let's say we're dealing with a frequency that's 1,000 hertz, and of course then omega, which is the angular frequency, would be, or radial frequency, which would be 2 pi times that amount, and that would be the frequency needed for this equation. Let's now plug those numbers in and see what we get. So how much is the displacement of the air under these circumstances? Or I should say the displacement of the air molecules. All right, so we have the maximum displacement in pressure, or the maximum change in pressure, is 0.02 newtons per square meter. We divided by the density of air, 1.29 kilograms per cubic meter. Multiply times the velocity, speed of sound in air, 340 meters per second. And finally, we multiply that times the angular frequency, which would be 2 pi times 1,000 hertz. Hertz, of course, is once per second. All right, 1,000 hertz is a typical frequency that you hear in human voice when we do singing. So I'm not going to sing for you though, wouldn't sound very good. All right, 0.02 divided by 1.29, divided by 340, and divided by 2, divided by pi, and divided by 1,000 equals, and there you have it. That causes a displacement, a maximum displacement of molecules in the air of 7.26 times 10 to the minus 9 meters, which is 7.26 nanometers. That's not very much. That's a very tiny displacement. So you only need very minute displacements of the air molecules to cause sound to travel through the air. That's actually phenomenal. 7.26 nanometers. That's much, much smaller than the wavelength of light, much, much smaller than any object that we're familiar with, like the human hair is much thicker than that. Wow, that's pretty small. Just to make sure, I'm going to calculate that again. Got the same number. Probably did not make a mistake then. Wow, that's pretty small. But anyway, that's how we calculate the displacement, the maximum displacement of the air molecules as they're vibrating back and forth as sound travels through the air. And that's how you do that.